The chain rule. Is it undoing the chain rule? Is that e to the 2x the derivative of kind of the interior of the bottom? No, it's not, right? It would be a sum of terms. Okay? So we look at this and we think, what is this kind of like? Do you see what this is kind of like? Yeah, so doesn't it kind of look like something squared over something squared plus 3, something plus 2? So you can see it looks like a rational function, but we've got e's in there, right? It's like a rational function. We've got e's in there. So it'd be really nice if instead we just had a rational function, say u squared over u squared plus 3u plus 2. Do you see how similar those are? What is u that makes those two equal? Those two integrals equal? E to the x, right? If I let u equal e to the x, then I get this. Well, actually, not quite. Not quite. We've got this du we got to take care of. As we saw in the first week, dx is not just kind of a signal that we're doing an integral. Dx is part of the math, right? Dx is part of the math. We said that thing's the rate of change, and we take the rate times a little change in x, which gives us a little bit of change of the quantity. So dx is part of the math. It's not just notation to mean, oh, this is an integral, this is an antiderivative. So that dx is important. We just can't change it to du. What is dx equal to? Let's take a look. If u equals e to the x, then du equals e to the x dx. Okay, so what does dx equal? So it doesn't equal du. What does dx equal? Du over e to the x. And what's e to the x? What do we call e to the x? That's what we said was u in the first place. So dx does not equal du. It actually equals du over u. Okay, so what we're talking about now is what's called a change of variables. This is a change of variables. We can look at that and think, oh, that kind of looks like a quadratic on the bottom, and this whole thing looks like a rational function if those e to the x's weren't there. So we change the variable to u. We say u equals e to the x, figure out what dx is, and now these integrals are equivalent, but they're just in a different variable. We call this change of variables. Change of variables. Okay, so now what can we do? We can say that u squared over u is just u to the first. Did that help us? Now, do we have some way to attack this? Some way to tackle this problem? Yeah. We could do partial fractions if what? If the denominator factors. Does it factor? So if it doesn't factor, then we can't do that. But if we have to have at least two factors. That's a real easy one. You should see immediately yes, that does factor. Okay, so we have this partial fractions problem. I'm writing too big. I'm going to run out of space. So this is a really easy one, so I'm going to kind of do it fast. I may streamline it a bit. What do we have? I'll do it in blue. So we're going to have a over u plus 2 do it up here. A over u plus 2 plus b over u plus 1. And we're saying that that's equal to this, right? We're saying that that sum, that blue sum right there, is equal to this. We got to figure out what a and b would be so that the numerator is just u. So when we add those fractions, we get a u plus 1 for the numerator plus b times u plus 2 with the common denominator right here. So what's our coefficient of u? Coefficient of u is a plus b, and that equals 1. Our constant would be a plus 2b, and that's equal to, this is like u plus 0, constant 0. So if you're, it's been 48 hours or so since we did partial fractions. So if you need to review, you need to review. But this says that minus b, I'm going to subtract. Minus b equals 1. So b is minus 1. And a is 2. So this thing equals integral of a is 2. 2 over u plus 2. Over negative 1 over u plus 1. Which is ln, 2 ln, absolute value u plus 2, minus ln, absolute value u plus 1, plus c. So we change the variables so we can do an antiderivative that we've seen before, something we can manage. But then when we're done, really what the problem was in terms of x up there, so we need to switch variables back. So that changing the variables helps us get the antiderivative more easily. And then once we have the antiderivative, we switch back to the original variable. So now we're going to switch back. So this thing right here is equal to 2 ln of what? E to the x plus 2, right? Because u is e to the x. Minus ln of e to the x plus 1 plus c. Okay, questions on this technique? So we change the variable from x to u to get something not so daunting looking, right? Manageable. And then we got partial fractions. We solved the antiderivative in terms of u and then switched it back to our original variable x by substituting back in e to the x equals u. Anybody have a question on this? Can I erase? I'm going to erase. Here we go. So let's try this. Well, it's kind of defeating the purpose here. Let's do this. It's the best integral sign I've drawn all day. Okay, here we go. So integral x minus 1 squared divided by square root of 1/2 x plus 1. First question we always ask is it undoing the chain rule? Is it undoing the chain rule? Do we have the derivative of the interior of the other part? Do we have the derivative f prime of the interior of the other factor? No, right? So this is not that. But we can do a change of variables. So what might we let u equal? So really, what's problematic here is the square root of a sum. Square root of a sum is what would prevent us from maybe expanding this out and getting a sum or difference of many terms. So if the problem is the square root of a sum, then what could we let u equal? That whole thing, right? 1/2 x plus 1. And so we're looking at getting square root of u. This is nice because if I get like a quadratic on the top, I can combine that with all three terms, and then it makes this kind of fraction go away. All right, so I want you to find dx. Okay, so we gotta find x, and then we find dx. Okay, if u is 1/2 x plus 1, find x and find dx, because we're going to need both of those things to rewrite the integral. So use your algebra, find x, and find dx. Go. Given the fact that u equals 1/2 x plus 1, it should be very easy for everyone in this room to find x. Find what x equals. And then from that, you find dx. A lot of people are just staring at the screen. Or you could consider dx equals multiplied. So instead we could have it written as du dx equals e to dx, and then you would multiply it with dx. Right, that's right. Now, that means that du equals e dx. Where's my pen? You should have gotten 2u minus 2 for x. 2u minus 2. Everyone in this room should have gotten 2u minus u. If we're having trouble with that, maybe we don't belong in Calc 2. That's easy algebra. All right, here we go. So dx equals derivative of this, 2 du. So that my order was a little different here. So I knew that I was going to need x, okay? And from x, it's more straightforward to find dx. In the last example, we didn't need x, so we just found du and solved for dx. But both are fine, okay? Just don't break any rules when you do the algebra, and there's no set way to do it. As long as you are mathematically correct, there's two ways to skin a cat here, okay? Questions on that? So now what does the integral become? Integral of? Over here. So our x is 2u minus 2 minus 1 squared over square root of That's what we wanted. Simplify up that square root. And then times 2 du. Do you follow what we did? Do you see why this is helpful? Do you see where we're going? How are we going to make this? Is it undoing the chain rule now? No, it's not. But we've got somewhere to go to crack this thing. What are we going to do? It's already factored, so you mean it's already factored. What do you mean? What can we do? Just algebra from here. It's just all algebra from here, just to get it into a form that we can take the antiderivative. It's all algebra. Yeah. Okay, we'll do u to the 1/2. Okay, u to the 1/2 negative. This isn't really changing anything, though. Yeah.
Can you pull out the 2 and then expand to u minus 3 and then set?
No, don't pull out the. No, just expand, right? You can't pull out a 2 when it's squared, right?
No, you pull the 2 in front of the.
Oh, that's fine. Yeah, it can be inside or out. That's fine.
And then expand to u minus 3.
Yeah, we're going to expand, right? We're going to multiply out the top, and what's going to happen? We're going to have a sum of terms. Sure. So we can put the 2 out front. That's fine. So 4u squared. 12u plus 9. Someone said change it to the u to the 1/2. That's fine. Do you see why this is helping? Why is this helping? What can we do next? Yeah. One more time. Yeah, so we're basically going to pull this apart now into 3 terms. Each one of those divided by u to the 1/2. So 4u squared divided by u to the 1/2 equals what? So if you want to start by multiplying up by u to the negative 1/2 and then distribute, that's the same thing. You could move this up to the top as u to the minus 1/2 and distribute. Or you can just separate the fractions. You got a single thing in the denominator. So that's the same as each one of the individual things over the denominator. 4u squared over u to the 1/2 is 4u to the 12u over u to the 1/2. You got to know your rules of exponents really well, okay, to do this. U to the 1 over u to the 1/2 is u to the 1/2 plus 9u to the, yep. Now we're ready. We can do it. 4u, so it's going to be what? 5/2, 2/5, u to the 5/2, minus 12, 2/3, u to the 3/2, just power rule. I'm just doing power rule here. Plus 9 times 2 u to the positive 1/2, plus c. 2 times all of those. Okay, but we have to, our original problem was in x, so we're going to have to change our variable back to x, according to u equals 1/2 x plus 1. So can I distribute and multiply and substitute back in all in one step? Can you follow that? I'm going to distribute the 2, I'm going to multiply out these coefficients with the 2, and put the 1/2 x plus 1 in, all in one step. You can do it. So it's going to be 8 16/5. 16/5. what? 1/2 x plus 1 to the 5/2 is the first term. What's the next one? 2 times negative 48/3. 2 times 12 times 2. Minus 48/3. 1/2 x plus 1 to the 3/2. Looks like the last one is plus 36. 1/2 x plus, check my math, Make sure you agree. Plus c. What is it? I'm not following. Oh, so you can simplify that? Yeah, 48, thank you. Yeah, so 48/3 is 16. Thanks. Any questions? Any questions? Does it make sense what we're doing? Okay, suppose this was from 2 to 7. So we could do exactly what we did, and then get to this last step, and now evaluate the antiderivative from 2 to 7. Right? So we do everything we did, and just take this thing I put a box around, put the 7 in, put the 2 in, and subtract. The total change, right? The total change starting at 2, ending at 7. But there's something else we could do. Another way to approach this for a definite integral. We could find the corresponding u values. What is u when x is 2? What is u when x is 2? Unfortunately, it's also 2. And what is u when x is 7? All right, it's going to be 7/2 plus 1. Is that 4.5? 9/2? So if it's the definite integral, we could go ahead and change the limits too from u to x. Sorry, x to u, x equals 2, x equals 7, to u equals 2, u equals 9/2. And when I got here, I could just evaluate this one from 2 to 9/2. And I wouldn't have to change it back into x. So when you have a definite integral, you've got that choice. You could do it like normal and then use the original limits on your final answer. Or you could also get the new limits in the new variable and then apply them to the u antiderivative, and you wouldn't have to substitute back. Does it make sense? Two ways to then, for a definite integral, if you change variables, you can evaluate the final answer in either variable. That's what I'm saying. Okay, questions on that? Okay, why don't you practice one, and then I've got one more thing to do, so this is not the last thing, but I'll give you a kind of one you can practice on. Just write it. So the first thing I'd like you to do is discuss what would be one small change you could make to this so that it would be undoing the chain rule. What would one small change that you would make to this so that it would be an undoing the chain rule? Because it is not. It is not. Okay? What would one small change be? And then after you figure that out, then work on this one. Don't change it. You actually evaluate the one I gave you. Okay? Go. And there's something else we need to do, so move. Let's just get started enough on it so we can see the light, and then we'll move to something else. So just a couple of minutes, just 2 minutes on that. Okay, check and see if you got the same thing. Hopefully most of us did. It's really algebra. It's just substitution. Substituting a new variable and expressions in for old ones. It's just algebra. Did you get that? Why does that help? Because this is u to the 1/3, and we can do what now? Distribute. Get two terms. U to the 4/3 plus easy from there. So antiderivative, change back to x. According to u equals x minus 2. Questions on this one? Okay, so there are some more complex forms for which you have a table of integrals in your book. But to use the table, you have to know this. You have to be able to, because you're going to have to often do a change of variables first to get it to look just like the tables. Let me show you the tables. Okay, so this is in the book, this is your table of integrals. So they got the basic ones at the beginning. All right, very, very basic. Okay, then there's a section starting at 30, trigonometric integrals. This is in the appendix of your book. Okay, so these are forms involving trig. Okay, so now look at these. So now we've got, I want to give you the example here that we're looking for. So write this one down. This is the one we're going to do. 1 over square root of x squared times the square root of 4x squared minus 7. Okay, that's the one we're going to do. Write that down. I'm going to go back to the table in a second here. Okay, got it? So now if you look, we've got, starting with number 61, forms involving a squared minus x squared, a being a constant. And then starting with 68, we have forms involving x squared minus a squared. Again, a being a constant. And then if I turn the page, the next section, form integrals involving a squared plus x squared. Sorry, up here. There, starting with 76. And then integrals involving ax plus or minus b, etc. So they're giving you a general form and telling you what the antiderivative is for each of these general forms. So going back to the example I gave you, which section of the table will that relate to? It's one of these recent ones that I did. So back on this other page. So there's integrals involving a squared minus x squared, integrals involving x squared minus a squared. Do you see that that's what it is? It's involving x squared minus a squared. So now we look at these, and we see which of these, 68 through 75, would apply to the one I gave you. So you see that it's 70. But it's a little different, so that's why we need the change of variables to make it look just like that. Okay? So ours is x squared times radical 2x squared. That's our problem. We have the 2 in front of the x squared. So we need to get just something squared, right? Just something squared, not 2x squared. Okay, so then how do we change the variables to do that? Where's my pen? Okay. So I gave you, so if we just want something squared, then what are we going to say equals to do this? Sorry, we're going to go over a little bit. Sorry. I'll give it back to you on another day. So I need to get just something squared, not 4x squared. So we can use u, that's fine. But what is u going to equal so that that's just u squared and not something u squared? So u has to equal what then? So do you see that it has to equal 2x? Do you see that? That's what you should have been. So u would have to equal 2x. Because what we want there is u squared. So if you're not sure, you could just say so we want u squared to be 4x squared and work backwards. Okay? Then what would u have to be? U would have to be 2x. Okay? And then what is, remember this was going to be something squared minus 7. So and that was the a squared. There's a squared. What is a? So a squared is 7. Then a has to be square root of 7. I suppose it could be negative 2, but let's just make it square root of 7. Okay, and then so now we need dx. So if u equals 2 dx, then du equals 2 dx. And what does dx equal? 1/2 du. So now we can rewrite this thing so that that's just u squared, and we can use the table. Use the table. So it's going to be 1 over, what is x squared? X squared is u squared over 4. Do you see it? What's 4x squared? That's our u squared. Minus square root of 7, we can write it this way, square root of 7 squared. And then times dx is 1/2 du. We had to get that 4x squared just to be a single variable squared in order to apply the table formula. So now we can get rid of this 1/2, and then this is really 4 in the numerator, right? 1/4 in the denominator is really 4 in the numerator with a 1/2. Altogether makes 2, right? So it's really the same as 2 times the integral 1 over u squared minus radical 7 squared du. So now we can use table formula 70. That's right, right? Wasn't it 70? Where we've got u and we've got a is square root of 7, and then the whole thing times 2 in the end. So now you just apply the table formula. And the answer is going to be what? It's going to be, that looks really weird. That's my hand. All right, so it's going to be square root of u squared minus 7 over 7u. And then we have to change back to our x according to what we called u. So you're just going to write down the antiderivative because we have it exactly in the form that they had it in the table, and then change your variable back.